Hello, good evening. Today is December 27th, 2020, and I'm Bhavani Thuraisingam from the University of Texas at Dallas. And as I mentioned in my presentation yesterday, I'm making a few video presentations this week, starting yesterday, today, and the next few days. And these presentations are some of the sort of important presentations I've given over the years. So before this, while working, before this set of presentations this week, I've been giving several video presentations between March and December, actually between May and December, because I didn't record the presentations before May. And those presentations were the keynote presentations I gave at various conferences while working from home during COVID-19. And so what I used to do was to make a placeholder presentation and then post it on YouTube, but also, give live presentations as much as possible. But the placeholder presentations were needed because just in case there was a technology glitch. And so I felt after I gave those series of presentations, mostly, I had 17 keynote addresses and 11 panels. So I probably would have given around, 22, 23 presentations. I also gave a few presentations on some key important topics. So those presentations were really current presentations, right, on current topics, such as Internet of Transportation infrastructures, as well as adversarial machine learning, so integrating AI, cybersecurity, and machine learning. And so these were some of the topics that I talked about between May and December. But this week, I'll be giving around 4 to 5 presentations. This is my second. I might also extend it to next week because our semester starts on January, so January 10th is when, no, not 10th, January 11th is when, we go back to work. And so then I'll, resume with my lectures, and then hopefully, whenever I give any external presentations, so those presentations will be more current. So yesterday I gave a presentation on malware, right? What is malware? What is it? And what can we do about malware? So that was more of a presentation, a general presentation that I gave at the Polycarp Kush lecture back in April 2013. That's a distinguished lecture that University of Texas at Dallas invites one professor to give a presentation every year in April. Polycarp Kush, I believe, was a Nobel laureate in physics. So to honor him, we have a presentation every year. So that presentation I gave in April 2013. And it was supposed to be a more general presentation because that's not for technical people, it's more for the donors and visitors and those from senior administration, non-computer scientists. And so I've given that presentation quite a few times to public libraries, to the general public, including public libraries, as well as to, like subcontractor association, mainly for non-computer scientists. Now, today's presentation is going to continue on malware, but it's more of a technical presentation. And I'm going to talk about data mining for malware detection. So it's based on a book that we wrote, and that was published in December 2011, Data Mining Tools for Malware Detection. That was the topic. Myself and my colleague, Professor Latifa Khan, and we had a PhD student, actually it was mainly Dr. Khan's student, who was later a postdoc. So it was a joint postdoc between Dr. Khan and myself. And so he's Dr. Mehdi Masood. And so Dr. Masood is now a professor at University of UAE, United Arab Emirates in Abu Dhabi. And so this was a joint, some joint research that we did, and we wrote a book. So this presentation is based on the book, but the book was also written after I gave a number of keynote presentations on this topic throughout, from the time I started at UT Dallas. It was in fall 2004. So I really started on this particular topic in 2006 through 2011. And so it was really 5 years worth of presentations, and we have lots of papers in top tier venues. And so more recently, our research has been, we don't sort of talk about data mining as much now. It's more data science, machine learning, AI. So I've given quite a few presentations on some of our work on applying data science and machine learning for cybersecurity applications, as well as adversarial machine learning. So what happens if these machine learning techniques are attacked? Okay, so, but as I said, this presentation is a presentation I gave in 2011 at the European ISI, European Intelligence and Security Informatics conference. Just want to make sure that the sound is working. Yeah, so European ISI, European Intelligence and Information Security. We also have General Information and Security, Intelligence and Security Informatics. And that's sort of more the US based. And so that conference is, it has been in, we had that conference, I believe, in Taiwan, in Beijing, as well as in Holland, but there's also Netherlands. Also, we have a European ISI. And then we also have a Pacific Asia, PICE, Pacific Asia Intelligence and Security Informatics. And so usually that conference is held in conjunction with PAKDD, the Pacific Asia Knowledge Discovery and Data Mining. Okay, so anyway, so that's going to be my talk. And so I'm going to share my screen. Okay, and so I have got this entire presentation up. Let's see. Okay. So it is actually in PDF version. Okay, so data mining for malware detection. It's again joint work, Dr. Mehdi Masood, Dr. Latifa Khan, and myself. It's mainly Dr. Masood's part of his PhD thesis. And we also wrote a book based on this. So today's date, is in December 2020. But this address, most of these charts, so much of this presentation was given as a keynote address at EUROISI. EUROISI is the European ISI conference, European Conference on Intelligence and Security Informatics in 2011. And that was given in September 2011 in Athens in Greece. So, right, so first I'll talk about, just briefly provide an overview of data mining, and then talk about the number of tools we have developed: intrusion detection, malicious code detection, buffer overflow detection, email worm detection, worms and viruses. And yesterday I talked about malicious malware. Malware is malicious software. So malicious software is sort of the general term, malware, which includes worms, viruses, Trojan horses, sort of everything. Then I talk about a particular technique that we have developed called novel class algorithms, novel class detection. And that's sort of, so all of the first part, we have developed techniques and tested them. The third one, we have developed a number of novel class detection algorithms, but not so much for malware. It was developed for NASA and various other applications for detecting faults in reports. So my thesis or my premise is that we can apply this for malware, malicious software. Only thing, we don't have a lot of data for polymorphic malware, malware that is mutating and changing patterns. Actually, yesterday when I talked about malware, I gave a good analogy between malware and the human virus. And especially these days, we are so, concerned and terrified about coronavirus, SARS-CoV-2, and the disease, COVID-19. And so I sort of discussed, drew an analogy between the two, but I'm not going to do it today, but you can look at my video presentation that I gave yesterday, and that's already up on YouTube. Okay, so novel class detection for polymorphic malware. And then as a reference, it's data mining tools for malware detection, published in December 2011. It's by CRC Press. It's now Taylor and Francis, Masood Khan and Thoresinger. Note, in 2020, as I said, we generally refer to data mining today as data science, okay? Fine. So what is data mining? So there are so many names, especially when it started in the 1989, 1991 and beyond. Some call it information harvesting, knowledge mining, data mining, knowledge discovery in databases, data dredging, data archaeology, database mining, data pattern processing, severe knowledge extraction. The process of discovering meaningful new correlations, patterns, and trends by sifting through large amounts of data, often previously unknown, using a number of techniques: pattern recognition techniques, statistical and mathematical techniques, machine learning techniques. So this was a book I wrote in 1998. It's a sort of fairly high-level book on data mining for CRC Press. Okay, so what's going on in data mining? Remember, I gave this presentation in 2011. Okay, lot has happened since then. So back in 2011, a lot of technologies, and even today we have all these technologies: database management, data warehousing, machine learning, statistics, pattern recognition, visualization, parallel processing. So remember, machine learning has been around for quite a while, right? It has been around since probably the 1960s, late 60s. Marvin Minsky talked about neural networks. You've got to go back to, I think, McCullough and Pitts in the 1940s. But in any case, machine learning, as we know, it started in perhaps in the late 60s and 70s, but they were not really being applied to real world problems, although there were expert systems being developed at that time. And I was at Honeywell in the mid to late 1980s, and I developed expert systems for process control systems. But then in the 80s and early 90s, we had technologies now to manage large databases, right? Again, by today's standards, those databases are really tiny, but then we were able to manage gigabytes of databases, and we were even getting into petabytes. But today, petabytes, every day we are collecting exabytes of data. So petabytes is just nothing today, but still we had some good data management techniques. So we were able to apply these data management techniques, data warehousing, and there was machine learning, parallel processing, and so on. And so we're able to integrate all of them and dig and mine the data and extract those nuggets. And so what can data mining do for you? It can do classification. It can cluster, classify the data, cluster the data, form associations, detect anomalies, prediction, estimation. And these are all things that machine learning can also do for you now. And how do you carry out data mining? So data mining techniques include decision trees. I mean, these are also machine learning, neural networks, of course, machine learning. Today we have deep learning techniques. Market basket analysis was something interesting. How did it start? It's actually association rule mining. So when you go to the supermarket, right, what you want to do is you make some purchases, right? Based on millions of purchases, you can sort of do generalization and say bread and milk don't go together. I mean, that's sort of not that exciting, because we know that bread and milk are sort of essential food items, or coffee and milk, or tea and milk, and so on. But then it'll be nice to extend it to people who travel together, or maybe find some unusual patterns, such as what are some of the unusual patterns that you don't expect, right? So let's say all bran and ketchup, right? Why would someone buy all bran and ketchup? But that could be something interesting, right? Or people who are traveling together, people who are, going places together. And link analysis, right? Forming links and associations and genetic algorithms. So these are all data mining techniques, right? And what is the current status? Remember, 2011, many commercial products, they were mining relational databases, but then we said the challenge is, of course, mining unstructured data. Today, we have good techniques to, mine unstructured data, such as multimedia, images, video, and so on, extracting useful patterns mining the web, and we can do that today. Data mining, security, and privacy, right? Privacy is still a big challenge. And also today with data mining, sort of with machine learning, explainable AI, explainable machine learning, how do you explain these machine learning techniques? So several advances today, but remember, this was 2011. And so data mining for intrusion detection. So now I talk about the various tools that we have developed, right? So one of the first tools that we developed, and this was mainly Dr. Khan's work, intrusion, and this was with one of his previous students, Dr. Awad. Intrusion detection can be defined as any set of actions that attempt to compromise the integrity, confidentiality, or availability of a resource. And so there are various types of attacks, attacks to the host, attacks to the network. Again, you have attacks to the web, attacks to the infrastructures, and today we have IoT systems. So intrusion detection systems are split into two groups, anomaly detection and misuse detection. So now anomaly detection, and I'll explain. So anything that is not normal is abnormal, right? Misuse is that, so okay, so anomaly, I always sort of think twice before I explain. So anomaly, okay, I'm going to talk about what these two things are, okay? Two types of intrusion detection. So we can use audit logs, capture all activities in networks and hosts, but the amount of data is so huge. So we have to come up with some efficient processing techniques. Okay, so here is misuse detection. So I'm talking about misuse first and then anomaly. So misuse is that we have all of the bad patterns. That means all of the attacks are stored in a database. And then we do pattern matching. And then when a new attack comes, a new pattern comes in, we say, is it an intrusion or not? And then if it is not in the database, we say it's fine. But that's a problem, right? So misuse means we have all the bad patterns, intrusions. So anything that is not in here is not an intrusion. So when malware is mutating or whatever, it won't catch it because it's not in the attack database. So to a great extent, it's helpful because it can find all the known attacks, but it cannot detect new attacks. So example, if IP source equals IP some destination, then land attack. Okay, so you cannot detect new attacks. That's the problem. But then once you detect whatever is in the intrusions, when you detect if it's an intrusion, then of course you stop, you quarantine. All right, so that's intrusion detection, misuse detection. The other, so all the bad patterns are stored in there. So anomaly detection, actually this is this picture is not quite what I'm saying. It's sort of more our performance numbers that I'm mentioning. But anyway, what we are saying here is all the good behavior is stored in the database. So that means like my behavior, like usually I sleep very late, 2, 3 o'clock, that's true, 2, 3 o'clock in the morning. And then I wake up around 8, 9 o'clock in the morning. Some days, of course, earlier because, if I have meetings, I try to keep all my meetings 9 o'clock and afterwards, preferably a little later. But so I try, usually, most meetings, they start, some of the meetings start at 7 because if it's East Coast, 8 o'clock in the morning. But in any case, the point here is that, so if somebody sees me, right, that I'm checking emails at 6 o'clock or 7 o'clock in the morning, it is very unusual, right? Because I wake up at, say, between 8 and 9, and then I have my tea, and by the time I start working, it's probably around 10 o'clock in the morning, and that's when I start usually checking all my emails, and that goes on till about 2, 3 o'clock in the early morning. So if somebody finds that I'm checking my email at 6, 7 o'clock, oh, it's not me, it's somebody else who's pretending to be me, because it's not in the database about my normal behavior. So anomalies, anything that is not normal is considered to be abnormal. Misuse, anything that is not abnormal is considered to be normal. Both have problems, right? Even anomaly, relatively high false positive rate, and also it can, anomalies can just be new normal activities. It could be that I have woken up at 6 o'clock in the morning and checking emails. It's not an attack. It's something that is really happening, right? So those are problems, but still, it's something that there's a lot of work that has been done and a lot of progress on intrusion detection. Okay, so what is our contribution? So we looked at support vector. Now forget about this particular box for a moment. We looked at support vector machine, right? It's divides it's a classification technique, divides the group into multiple classes. So we look at two classes. Is it a good class or a bad class? And so we have training data and we train, and then of course you test, and is it a good class, bad class? Anomaly, is it an attack? It's not an attack, right? So we looked at support vector machine, but our contribution, and particular Dr. Khan and his student, Dr. Awad, is hierarchical clustering. So DGSOT, dynamically growing self-organizing tree. And that significantly improved performance. So what is that? Very briefly, so you have two classes, hierarchical clustering. So when you build these decision trees, support vector machines, right? And decision trees, you can go right down. I mean, you can go on and on and on. The tree could be really, really, really long, and it takes a long time. So you have to find an appropriate level, and then you have to prune, and then you train the support vector machine at that right level. And then what is the stopping criteria? Are we ready to stop? No, then we have to decluster and then continue the process. Otherwise, we are done. So it really improves the performance and accuracy of the support vector machine. So at that time, remember, this work was done around 2004, around 2004. So we looked at number of techniques, the random selection methods, pure support vector machine with somebody else. So there was another group, Rocio bundling. They looked at support vector machines and made some modifications, and we worked on DGSOT. So you can see and we looked at, we try to duplicate all the environment, the programming environment. And so you can see random selection accuracy was kind of, only 52%, pure support vector machine, 57.6, Rocio bundling was 51.6, and we had close to 70%. Training time, of course, random is very short time, 0.4 for less than an hour. Support vector machine 17.34, and with Rocio bundling was 26.7, and DGSOT was 13.18. And then false positives, you can see random selection 40%, false positive 47, false negative, support vector machine 35.5% false positive and 42% false negative, and Rocio bundling 44.2% false positive, 48% false negative, and then DGSOT 37.8% false positive and 29.8. So we had much better accuracy, false positives, false negatives. And also when I presented these results, first time at an invited talk at King's College, the conference that was going on, April 2006 at King's College, University of London. I think that was the first time I gave this particular version of this presentation. And so there was someone in the audience said, right, 33% is still, or 37, 20, 30% is not acceptable. Yes, it was not acceptable. But remember at that time, I mean, if we published this in a top tier venue, and so it was accepted because at that time, to get 30%, sort of 70% accuracy was actually quite good. Today, we are expecting like 95% accuracy. And in fact, we are looking at, like 2% of accuracy, error rate, like about 2%, which is very, very low, right? So because technology has advanced so much. Okay, so that was intrusion detection. So what did we do next? Next, we said there were a number of tools, and this was, as I said, our book on data mining tools for malware detection. And so I still remember, I just wanted to say something, it was going back memory lane. So right now I'm working on our book on secure data science, okay? So 10 years ago, December, during our Christmas break, the holidays that we have, that's when I was working on this book with Mehdi. So I would be working and sending him chapters. And so it was really, really interesting. And then, so we finished all our chapters by January, and then we had a draft, a good final chapters like by March or April. So I can remember 10 years ago, we were working. And so did I ever imagine 10 years from now, I'll be still working on another book, although, it's with my colleagues. But then that I'll be working, from home. We are all going to be working from home with COVID-19, sort of not sure what the future is going to be, right? But still, I'm doing these videos. Okay, at the end, I'm going to give a short presentation about, how we can also sort of a comparison to COVID-19 and also what we can do to, be positive about, about these difficult times that we are having. Okay, so what are malicious executables? These are malicious code, malicious software, right? And yesterday I explained quite well in my presentation what is malware. It's just a piece of code, right? It's just like a software program, but this is malicious program. And when you execute it, it's devastating. And when does it get triggered? The perpetrator is watching, right? He or she unleashes his malware. It gets into your machine, stays there dormant. And when he's ready, he can unleash it or trigger something immediately, right? It can cause havoc. So malicious executables, right? They harm computer systems, and viruses exploit denial of service, flooders, sniffers, spoofer, Trojan, we just call malware now. Exploit software vulnerability on a victim. Victim is the victim machine. May remotely infect other victims, incurs great loss, and Code Red 2001. That's when a lot of bad things happened, because not only we had 9/11, that's when people started taking cybersecurity very seriously. Epidemic cost $2.6 billion. Malicious code detection is a traditional approach, right, which is signature based. Looking at the signature of the malware requires signatures to be generated by human experts. So not effective against zero-day attacks. So what happens if you have a new malware that comes in, right? It's not going to detect it. So that's the challenge we are faced with today, 0 days, malware that is mutating, okay? So that's what happened. So what did we do? So again, what are the approaches? Automated detection approaches. You can do behavioral analysis, behaviors like source, destination address, attachment, what is other attachment types, statistical anomalies, and so on. And then you can do content-based, analyze the content of malicious executables. So there are a couple of methods. Autograph by Kim from Carnegie Mellon, based on automated signature generation processes. And then you also have Engram Analysis, Maloof, based on mining features and using machine learning. So our approach is very interesting. So we said content-based approaches consider only machine codes. So some of these approaches consider only byte codes, 1, 0s, bits and bytes. So we said, is it possible to consider higher level source codes for malicious code detection, like assembly language? Yes, because we have disassembly programs, right? You can take binary and go into assembly. And now you can also go from binary, hopefully, to high level languages, right? But again, there are some errors there, but there are good disassemblers. Extract important features from assembly program and combine with machine code features. So see, at that time, that's why we need this explainable AI, because at that time, it was sort of, it was a bit of a challenge, because we didn't know why we were doing things. It's sort of in a way like cooking, right? In the sense that you have to put these different ingredients. Maybe you have put a bit more cinnamon or a little bit of cumin or garlic, maybe a little less garlic. So things like that. But we want to get a scientific explanation why it's behaving in certain ways. And so now I think, especially with this explainable AI, we will have a lot more information on why machine learning algorithms are doing certain things in certain ways. Okay, so feature extraction in the hybrid model. So what are the features? So we use binary engram features. So sequence of n consecutive bytes of binary executables. We can also use that's for the binary code. For the assembly code, we also have engram features, a sequence of n consecutive assembly instructions. And you can also have API, application programming interface call level features, and then collect training samples of normal and malicious executables. A number of training data. There's lots of training data on the web for this kind of application. We extract features, train a classifier, build a model, and test. So it's training and testing. Okay, so as you can see, the test training phase, machine executables, bytecode to take the bytes and extract the engrams, and then apply the disassembler, get the assembly program, and also get the engrams. But then numerous engrams, millions and millions of engrams. So we do use some formulas that's already out there, and we select the best engrams and combine, and then develop the feature vectors, and then we do the training, and then we have the classifier. Then for testing, we take the executable, we disassemble, there's an assembly language, assembly program, and then compute the vector, feature vector, and then test the classifier. Okay, so assembly program, as well as we can also use the binary program. So this is the process. Okay, so feature extraction. What are the binary engrams? Features are extracted from the bytecodes in the form of engrams where n equals 2, 4, 6, 8, 10, and so on. Example, given an 11 byte sequence. Remember, bytes, right? So byte is, so it is 0, 0, 0, 0, 0. So 11 bytes. So this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 8 bits. So 0, 0, 0, 0, 0, 0, 0, 1, and so on. We know 9 is 1, 0, 0, 1, and A then would be 10, right? 1, 0, 1, 0. B is 11, C is 12, D is 13, 14, 15, right? So 11 byte sequence. You take 2 grams, 2 byte sequences are 0, 1, 1, 2, 2, 3, 4, 5, 4, 5, 6, 7 in this, 6, 7, 8, 9, 8, 9, AB, and so on. 4 grams is 0, 1, 2, 3, 4, 5, 6, 7. So it's 0, 1, 2, 3, 4, 5, 6, 7. Okay. So problem, large data set, millions of features. So we can use some secondary memory efficient data structures and apply feature selection. And right, so I'm going to come back what formula we are using in a minute. So assembly, again, very similar. Features are extracted from assembly programs in the form of engrams. N is 2, 4, 6, and so on. So the instructions are push some register, move one register into some other location, add one register to another register. These are typical assembly language programs. Today, I don't know whether we teach assembly language, but when I was in grad school, I took classes in assembly language. I think we learned Motorola. Actually, I was teaching Motorola 68000. And we took our assembly language class was, I think PDP 11 was the machine, and we used the assembly language for that machine. I cannot remember. But I taught Motorola 68000 when I was an adjunct faculty and teaching assembly language classes when I was working in the industry in Minneapolis. I was also an adjunct professor at the University of Minnesota. Anyway, and that was in the 1980s, right? 84, 85, 86, and so on. But now I don't know whether we teach assembly language programming. Anyway, so 2 grams would be push EAX, move EAX to D word, and so on. So again, many, same numerous engrams, and so we have to come up with an efficient solution. So we want to select the best K features, and there's already something in the literature for information gain. Gain of an attribute A on a collection of examples is given by gain SA, which is the entropy. Entropy is the information content. If you read Shannon's communication theory, that talks about entropy, right? And so you talk about entropy, there's information content. So what is the amount of information that any piece of data contains? So he has a beautiful way of explaining this whole concept of entropy. So by attribute A, you want to keep the attribute A, right? So gain of an attribute A on a collection of examples S is given by the entropy of S minus, right, the values in A, SV over S, mod of SV over S, entropy of SV. So for all values in A. So we compute the entropy. And so that will give you, is A useful or not, right? So I'm not going to go into the equations. We didn't come up with it. It's already out there. So we use that equation and then selected the features. Okay, so what are the data sets we used? 802 data sets. So 838 malicious and 597 benign. Data set 2, 1082 malicious and 1370 benign. And then our disassembly, we used the PED disassemb. And then training and testing, we had support vector machines. And then the second algorithm, C support vector classifiers with an RBF kernel, 2 algorithms. Okay, our results, hybrid approach, hybrid feature set. So you can see, and this is so you can see, right? Hybrid, all these engrams. We had, I think this is the accuracy, 96%. Binary only engrams, 89.83%. Assembly only 86. So hybrid was more accurate. And same thing for our data set 2 as well. Here again is support vector machine. Hybrid was 96.15, BFS, and binary and assembly. So hybrid performed. And then this was our second algorithm. My first one was support vector machine under the ROC curve on second algorithm. So again, we looked at, I think, the accuracy. So hybrid was 99 and BFS binary 0.93, assembly 0.93, and for data set 2 as well, we got, I think, better, right, 99%, 93%, and 92%, so better accuracy. Okay, so table 3 is false positives, false negatives on, I think it was probably for support vector machines, I think, the algorithm. And so hybrid false positives, say n equals 10, right? So let's look at the average engrams we took from 1 to 10. So 5.4 false positive, 2.6 false negative. For binary only 17.8-4.7. And the assembly is 24.4 false positive, very high, and 3.3 false negative. And for data set 2, very similar. We had 3.9/3.6 and 16.1/8.9, 18.1/9.8. So our hybrid worked much better. Okay, so that is our second tool. So we talked about the intrusion detection tool. We talked, oh, by the way, the intrusion detection tool was not in our book, Data Mining for Malware Detection. The intrusion detection tool was published in an earlier book. So in 2009, we published a book, myself and Professor Khan, with 2 other PhD students. One is Dr. Awad, who developed the intrusion detection, and the other one was Lei Wang, Dr. Wang, who developed the image mining, right? Annotating images and image mining. So the name of that book was Design and Implementation of Data Mining Tools. So because one was security, right? What Dr. Awad developed, and what Dr. Wang developed was sort of just multimedia mining, right? So that was a first book Dr. Khan and I wrote together. Well, I've written some other books before that. And then this was our second book together. And we have written, I think, one other book, and now we are working on the 4th one together. Okay, so data mining for buffer overflow, intrusion detection. Okay, so now another tool, buffer overflow. So overflow problem, it's a big problem. Intrusion detection, we talked about goal. How do you detect intrusions or malicious attacks, worm attacks, and so on, and buffer overflow attacks. The main contribution, worm code detection by data mining coupled with reverse engineering. Buffer overflow detection by combining data mining with static analysis of assembly code. Okay, so what is buffer overflow? Buffer overflow can happen during some errors in programming, but often it also happens due to attacks. A situation when a fixed size buffer is overflowed by a larger sized input. How does it happen? So you're executing a program, right? Then you have a subroutine. When you come to the subroutine, you've got to branch into the subroutine, execute the subroutine, come back and continue executing. How do you know where to come back, right? All the values and the variables, X equals something, Y equals something, Z equals something, you've got to come back and use the original values. That's where you store all of those values into a buffer, so that when you come back after executing the subroutine, you know where to get the information from the buffer and continue. It's just like you are doing some task, right? Sorting out papers. Oh, and suddenly you go out, you go away, and you want to do some other task, and then you come back, and now you want to sort out the papers, right? And so, but how do you know where you left off? If someone has come and disrupted everything, absolutely you don't know what to do. And we're talking about, lots of papers you're sorting. So it's just very much like that. So what happens is that, so when you come back, you can pull all the stuff out and do it. In the meantime, what happens that if an attack comes in and overwrites the buffer, then you don't know, the whole system will crash. Okay, so sometimes you say buffer overflow attack, you can get some error messages when you do some web surfing. I used to get it quite often those days, which I don't get it now. Those days means even as early as probably 13, 14 years ago. Okay, so problem with buffer overflow, you have okay, so you have, right, so that's essentially what I said. Buffer, you have a stack, right? Buffer and stack, so you put everything, all the stuff into the buffer and stuff, it's stack, it's all in the memory, and this is your return address. That's where you come back and you resume things. But what happens is that attacker has attacked in the meantime. So new return address points to this memory location, and there's absolutely all your values are gone. That's what is happening. So what do? Handling buffer overflow. So stopping buffer overflow, there's preventive, there's detection, finding bugs in source code, so examine the code and find the problem, can only work when source code is available. Often we don't have the source code. So compiler extension, same problem. Sometimes OS, operating system hardware modifications, people are trying to do buffer overflow these days in hardware. Detection approaches, so we prevent it, better hardware. Capture code running symptoms, problem may require long running time, automatically generate signatures of buffer overflow attacks. So what did we do? So this is joint work with Penn State University. Why did we do it with Penn State? Penn State, Dr. Peng Liu, top expert in this area, and they had developed a system called SIG-free. Okay, so, and they only considered binary code. So we said, look, let's try our approach, binary and assembly together. So that's the strength, our strength. So detection based on observation. Okay, so that's one. So joint work with them. And so we said, through our common sense, and not just common sense, looking at observing various attacks, attack messages usually contain code, software that can execute and cause damage, while normal messages contain data. It's not always the case, but very often we find that. So main idea, check whether message contains code or data. When that happens, then we break it down to a classification problem. Code, data. Problem to solve, distinguishing code from data. Formulate the problem as a classification problem, code or data. Collect a set of training examples containing both instances. Train the data with the machine learning algorithm, get the model, test this model against a new message. Enhanced Penn State's earlier model, SIG-free. Okay, so code, so our approach is code blocker. And so we have training data, we do disassembly, and then feature extraction, feature collection with Engram and control flow analysis, feature collection, right, with Engram and control flow analysis, and then feature collection with info gain. Okay, so that's training data. So very similar approach that we have mentioned earlier, Engram analysis, and then of course, best features and feature set. And then incoming requests, we do testing, right, disassembly, compute feature value, features in the feature set, and feature vector. That's a testing mode, so training and testing. Okay, so features are extracted using Engram analysis. We can, and remember, programs also have control flow, go-to statements. So we do Engram analysis. What is an engram? As I said, sequence of n instructions. Traditional approach, flow of control. Traditional approach, they don't take flow of control. So we took flow of control too. Okay, 2 grams. So these are the assembly language, right? XOR, the value in 2 registers, I think, move one to another, and so on. So 02, 24, 46, 69, 96, CE, sorry, 9C, CE. So we don't take the moves, right? So remember, when you come to 9, you can go to 9A or 9C. So assembly program corresponding control flow, IFG. Okay, so control flow based Engram analysis. What is Engram? Sequence of n instructions, proposed control flow based approach, flow of control is considered. So 2 grams, so it gets 02, 24, 46, 69, it has gone to, 69, 9C. We can also go to 9A, and so CE, and then you go back to E6, and so we have to take that into consideration. Okay, control flows. Here, no control flow and control flow based Engram analysis. Okay, what are the features? Control flow analysis, generated features, invalid memory reference IMR, undefined register, invalid jump target, checking IMR, a memory is referenced using register addressing and the register value is undefined, move AX, DX plus 5, checking UR, undefined register, check if the register value is set properly, checking IJT, check whether jump target does not violate instruction boundary, okay? So putting it all together, why Engram analysis? Intuition in general. Disassembled executable should have a different pattern of instruction usage than disassembled data. Again, data versus code executables. Why control flow analysis? Control flow analysis, there should be no invalid memory references or invalid jump targets. Approach, compute all possible engrams, select the best K, remember using entropy, compute feature vector, binary vector for each training example, supply these vectors for the training algorithm. Okay, data sets, real traces of normal messages, real attack messages, polymorphic shellcodes, training testing, support vector machines. So data distribution of attack messages in training and test data. And so attack messages, these are the malicious code, ADM mutate, clet, pex, oh, just a bit, I'm going to sneeze, I'm sorry. Sorry about that. Thank goodness there's no one in the room. Otherwise, imagine people will be terrified these days when somebody is sneezing, right? So anyway, so training and testing, support vector machines, right? So that's what we used. And here are the attacks. AD mutate, it's a malware. Testing, we had 265 cases, and then test cases, we had the training cases, 265, test 235. Similarly, we had clet, pex. This is all the malware. And the number of cases, the examples that we had for our training and testing. Okay, so the results we got, CFBN control flow based engram feature, CFF is control flow feature, and comparing performances of CBFN, control flow based engram feature. Let's say n equals 1 and through 5. Accuracy, you can see 91.4%, false positive and false negatives, right? So this is comparing performances among different features and SIG-free, right? Our algorithm, I believe, sorry, this is the control flow, what we got, and our code blocker with SIG-free. So code blocker, you had SIG-free, for example, accuracy was 69.4%. For code blocker, we had two, right? Control flow, and the other one was control flow feature. There were two ways that you can do it, right? So we looked at accuracy, 91.9%. The CFF technique was 87.4%. And when we combine it, so false positive, and then we had false negative. When we combine the two, we had false negative, we had 16.0, false positive is 0.3, and then the accuracy was 92.2. Okay, and then when you look at SIG-free with only binary engrams, their accuracy was a lot less, 69.4, and false positive, they were slightly better, there was 0, and false negative was really bad for them. Okay, so we got much better performance. So these were the results. Novelty, advantages, limitations, future. Novelty, we introduced a notion of control flow based engram. You take the control flow, that's CFBN, and the other is CFF. We combine control flow analysis with data mining to detect code data, significant improvement over the other method like SIG-free. Advantage, fast testing, signature-free operation, low overhead, robust against many obfuscations. Limitations, need samples of attacks and normal messages, may not be able to detect a completely new type of attack. Future, find more features, apply dynamic analysis techniques, semantic analysis, and so on. Okay, so that's the third tool, right? First, intrusion detection. Second was what? We had the malicious executable. Third was buffer overflow. Okay, so now email worm. So for email worm, task, given some training instances of both normal and viral emails, induce a hypothesis to detect viral emails. Emails are such a source for attackers to send attack messages, right? So we looked at all the outgoing emails, extracted features, training, we applied machine learning, and then we developed the classifier, and then new email comes in, and then we have the test data, and then it's clean email or infected email. And our algorithms were naive Bayesian and support vector machine, 2 machine learning techniques. This is our approach. Okay, so assumptions, features are based on outgoing emails, different users have different normal behavior. Analysis should be per user basis, 2 groups of features. We had per email, number of attachments, HTML in body, text binary attachments. Per window, mean words in body, variable words in subject, total of 24 features identified, identified normal and viral emails based on these features. Okay, so the feature sets per email, binary valued features. So does it have HTML? Does it have script tags and attributes, embedded images and hyperlinks? The presence of binary text attachments, MIME types or file attachments, meme types. Yeah. Continuous valued features, number of attachments, number of words, characters in the subject and body. Per window features, number of emails sent, number of unique emails recipients, number of unique sender addresses, average number of words, characters per subject, body, average word length, variance in number of words, characters per subject, body, varied in word length, ratio of emails with attachments. So these are the window features and the email features. Okay. And then we used collected data from UC Berkeley, contain instances for both normal and viral emails, 6 worm types. The worms were, remember, today we call the worms malware, right? Bagel, Bubbleboy, MyDoom, MyDoom.m, MyDoom.u, Netsky, and Sobig. Originally 6 sets of data. So training instances, normal was 400, 5 worms, 5 times 200. Testing instances, normal 1200 and a 6th worm. Problem not balanced, no cross-validation reported. So we rearranged the data and applied cross-validation and some analysis. I don't have the numbers for this particular experiments, but we did we looked at both the algorithms, naive Bayesian and SVM implementation. Naive Bayesian assumes normal distribution of numeric and real data, smoothing applied, support vector machine with the parameter settings, 1 class SVM with a radial basis function using gamma 0.15 and nu is 0.1. So analysis, we said naive Bayesian alone performs better than other techniques. Support vector machine alone performs better if parameters are set correctly, right? MyDoom and VBS Bubbleboy data are not sufficient, very low detection accuracy in all classifiers. That's the 3rd finding. The 4th, we said the feature-based approach seems to be useful only when we have identified the relevant features, gathered enough training data, implement classifiers with best parameter settings. See, data mining, machine learning, it's only as good as the features that you select. So feature selection is really crucial. Okay, so these were the 4 tools: intrusion detection, malicious executable detection, then we did buffer overflow detection, and 2 and 3 are somewhat similar. We looked at engrams. Anyway, number 4 is email worm. So now we talk about the big problem. What do we do when the malware is mutating? Malware is evolving continuously. So we did a lot of work on RAMAL, my colleague, Dr. Kevin Hamlin, reactively adaptive malware. We call it RAMAL, R-A-M-A-L. So we said novel class detection. We have a patented algorithm called SNOD, stream-based novel class detection system. Can we apply SNOD to RAMAL? And our tool will say, we'll call it SNODMAL. Okay, so that's the future. So what are we doing here? Signature-based antivirus protection is increasingly challenged because unless you have all of the signatures, when your code is changing, when your malware is changing, it won't detect, right? Polymorphic malware, by potential self-mutating malware to be emerged in near future. So we wrote a paper, very interesting paper in Computer Standards and Interfaces. What we did here was we applied data mining. Malware itself is applying data mining to determine how it's going to change patterns. So it's looking at the antivirus antivirus, all the virus signatures in the database. It's querying, and yesterday's presentation talked about it. It's querying those databases, and it's applying machine learning, data mining to and see how we can obfuscate and evolve, right? So we've got to combat that, because our adversary, the malicious code, malware, is using machine learning, and we have to then combat that. So that's why we've got all this adversarial machine learning. Anyway, antivirus must adapt itself to changing environment. For example, attacker strategies change over time. Therefore, characteristics of malware also change continuously. Signatures must be generated automatically to protect against polymorphic self-mutating malware. New types of attacks should be detectable by antivirus to guard against zero-day attacks. That's the biggest challenge, because it's just like, remember, the coronavirus, right? SARS-CoV-2, that's causing the deadly, COVID-19. So that's mutating, right? Recently, a week ago, we heard that there was a mutation found in UK. And so just like we are saying, antivirus products, will it work for mutated malware? We are asking the vaccines that were developed, right, based on the earlier genetic markup of the SARS-CoV-2, does that still work on the mutated virus, right? So similar questions we are asking here. That's the problem. So we said our SNOD algorithm, stream-based novel class detection. So lots of data coming in, streaming data. As streams come in, the concepts are changing, right? So today it's Microsoft, by Microsoft, tomorrow by Google, day after by Amazon, the next day by Apple, the next day by Facebook, next day by IBM, next day by Oracle. It's all changing. So we have to, so instead of having one model, because the models could soon get outdated, so we are developing an ensemble of models, and then these models are working together, applying machine learning, and then throwing away the models that are no longer valid and continuing. So when new data comes in, if it cannot be put into a bin, so if we cannot classify it, right? So what do? We put it into a buffer. Over time, it's not a question, suppose we know there are only two classes, red class and a blue class. But then there could be a totally unknown class called XYZ, could be purple, say, XYZ. So if it doesn't fit into A, sort of red class, if it doesn't fit into B, blue class, it could go into a new buffer. Eventually, we can see the patterns of all the stuff that's going into the buffer and say, look, we have a new class, XYZ. So that means if it doesn't fit into some of our signature malware, we are saying, okay, it goes into a new buffer. And over time, we say, oh, this is the signature of a new malware. So this is a new malware. That's what we are trying to do. We are developing SNODMAL, a malware detector using SNOD. Differences among different malware detectors, signature-based, right? It can do it cannot do anything. Automatic signature generation, zero-day attack, polymorphism, metamorphism, evolution of malware, benign executables over time, designed to detect new kind of attack. No. Traditional data mining based, you can do the first three, maybe some zero-day attack, polymorphism, metamorphism, and so on, but some others we can. We believe SNODMAL can do everything. So we try to do some work. So this is our algorithm, right? SNOD. Divide the data stream into equal chunks, train a classifier from each data chunk, keep the best L such classifier ensemble. Example for L equals 3, D1 may contain data points from different classes. So label chunk, unlabeled chunk, address infinite length. So you have, as D1 comes, you classifier C1, D2 classifier C2, D3 classifier C3, but they have thrown it off. Actually, because it's in PDF, I cannot show the animation here. Sorry about that. I should have tried to find my PowerPoint presentation. And so D5 as C5, because we have thrown D3 and D4 away, right? Ensemble, remember, so it must have been D1, D2, D3, and then D4 comes in. Some order when D4 comes in, I think we might have thrown D3, and then D5 comes in. D4 was maybe not current, right, outdated, so we threw D4, and so now we have classifier C1, C2, C5, and over time, D6 is our new buffer, right? We don't know yet, and over time, right, we will come up with a classification for D6, okay? So these are the classifiers and these are the data chunks. Okay, so that's our algorithm. And our architecture for SNOD-MAL framework, stream of benign and malicious executables, temporary training buffer, we put it in temporary buffers if we cannot find a place, feature extraction selection, training a new model, ensemble, remember we have an ensemble of models. So we have an ensemble of L models and we update it, we throw away some old models. And then we have, we classify malware, benign, novel, and then unknown executable comes in, extract features, is a testing, and then we know, is it a novel class, is it malware, is it benign? So this is something that, okay, so why didn't we continue with this work? Because we didn't really have enough data. We didn't have data for training because remember, we don't need traditional type of attack data. We need attack data where the malware is changing patterns. And that's where SNOD-MAL will perform at its best, is what I believe, right? So we don't have appropriate data to do the testing and training. Okay, so the usefulness of SNOD-MAL, capable of handling, this is what we believe, massive amounts of volumes of training data, also handles concept drift, concepts are changing, capable of detecting novel classes, new types of malware, existing techniques may fail to detect new types of malware, the current techniques, SNOD-MAL should be able to detect new type of novel class. SNOD-MAL will then quarantine the malware and raise an alarm. The quarantine binary would be analyzed by human experts. The classification model would be updated with new malware. Yes, therefore reduces damage caused by zero-day attacks. Use of cloud computing, right, for performance enhancements of feature extraction makes it more applicable to large volumes of data and optimizes running time. Okay, directions. Now this chart, I added, all of the other charts are old charts, right? I added a new chart, December 2020, based on all the developments over this last decade. Remember, we wrote the book, 10 years ago. And so, as I said, December 2010, right around this time, I was working with our postdoc, Dr. Masood. So 10 years later, where are we? Data mining has now evolved into data science, machine learning, AI. DSML AI being applied to detect malware. And we have, I give a lot of talks on insider threat in big data streams. Okay. DSML AI, these techniques could be attacked. That could be devastating because AI is being used for everything, right? For healthcare, for finance, for retail, for marketing, for drug discovery, maybe for COVID-19 and for cybersecurity attacks as well, right? That's what I say here. What happens if these AI techniques are attacked? We cannot trust in these AI techniques if they are attacked. And so we have to be one step. So adversary is trying to learn from us and trying to adapt its behavior. We have to be ahead of the adversary. And that's come to be known as adversarial machine learning. Malware may change patterns. Sorry, it's patterns, not patterns. Okay, sorry of the spelling. Malware evolution using DSML AI techniques. Cyber threats are increasing exponentially, need innovative solutions. Okay, so malware is changing patterns, as I said. Cyber threats are increasing exponentially, need innovative solutions to combat these threats. Emerging technologies, cloud, IoT are exacerbating the problem. Cloud can be used too, like what I said earlier, cloud could be very useful. Let's see, for performance intensive applications, but cloud can also be attacked. IoT can be attacked, right? So major challenges for cybersecurity researchers, developers, and practitioners. Okay, so we wrote a book, and that was about 2.5 years ago, and that was based on, here's the book. Oh gosh, I don't know whether I can show it. It's Big Data Analytics with Applications in Insider Threat Detection, published in 2017, December 2018, January. It's myself, Turesingham, my PhD student, former PhD student. She's Dr. Pallavi Pavin, and of course, Dr. Mehdi Masood. He's an expert in novel class detection and stream data mining, and Dr. Latifa Khan. Okay, so that is right, big data analytics with applications in insider threat detection. And right now we are working on secure data science, which is sort of applying data science for security, and applying security for data science. So this security means what happens if the data science techniques are attacked. Now, this book does not talk about adversarial machine learning, but our new book that I'm working on right now, that's talking about adversarial machine learning. Okay, so these are the directions. Okay, so I'm going to stop sharing. And so what have we studied so far? Okay, so what we have studied, what have I discussed so far? So what's happening is that we have, malware, right? What's the similarity between malware and this COVID-19, as I mentioned, right? So we have COVID-19, it's also it's a virus. And so it's going into, it's infecting people, it's replicating, it's infecting once one person is infected, it can infect other people, and then it's mutating. Similarly, the malicious software, it replicates, it mutates. And so, very similar situations. Only thing with COVID-19 and SARS-CoV-2, we are talking about biological human viruses versus computer viruses, life or death versus losing all your information and everything, right? All your privacy and everything getting lost, right? So there's a lot to learn from what's happening today with COVID. Both can learn from each other. So I gave a keynote address at Big Cyber, and that was earlier this month, where I talk about how we can learn from each other. Okay. And so another thing that I wanted to also mention is that, we have, the problem is that we are so preoccupied these days with COVID-19 that we are not really paying as much attention to cyber hygiene, right? Are we encrypting? Are we making sure that we are, backing up all our data? So we are not paying as much attention to cyber hygiene. As a result, we may have more attacks. So we've got to be very careful, just like there could be terrorist attacks, right? Because we are so concerned about our health. Of course, this is life or death, but we also have, right, about our cyber hygiene, so that, we take all the precautions and not let the hackers, get into our systems and steal information. So that is really important. And what was the other thing that I mentioned? I think I was going to talk about something, it was kind of something interesting I mentioned earlier about malicious, related to malware. I think, yeah, one was the similarities between malware and the viruses like COVID-19 and so on. And, we can also learn from, as I said, what we are doing. So that's one thing I wanted to mention. And then the other thing I wanted to talk about also was, we've got to be vigilant during this time. And so if you look at some of my other videos that I presented over the last several months, that was more on, adversarial machine learning. And then I also talk about data science for stream analytics for detecting malware. So what I'm saying is there's going to be, as technologies are being developed, right? IoT, Internet of Transportation, there's going to be more and more attacks. So we have to continue with our research, right? So it's, as I said yesterday, the medical doctors, right? They take their oath and they have to, take care of the patients, and they are really dedicated. They work hard, at least most doctors, and they work hard. And they, imagine if we didn't have all these doctors and nurses, not just doctors and nurses and all the healthcare professionals, what will we be doing today, right? So in the same way, although we computer scientists, cybersecurity experts, though we do not take sort of an oath that the medical doctors take, but we also have a commitment, because we've got to continue with this research, continue developing these tools, because, whether we like it or not, we have all these technologies. We cannot go back to 1960, 1970, even 1980 or even 1990. We have come so far, and we are only going to move, forward. And remember, if we didn't have all of these technologies, right, with COVID-19, what do you think would have happened? Most of us would have gone bankrupt, because how are we going to continue with our jobs, right? So without a doubt, technology is critical. And we know that with technology, we know what technology has done for us during COVID-19. And even social media, okay, that's what I wanted to mention. So even social media, the technology has helped us so much with COVID-19. Of course, we don't want fake news, right? That's very bad. But it's helped us, about giving us all this information. But more importantly, social media has also helped us to connect with people. Otherwise, how are we going to connect with people when we cannot, see them? We cannot have sort of in-person meetings or in-person parties or in-person get-togethers. So how are we going to connect with people? So social media has given us an opportunity. And that way, social media has given us ways for us to sort of connect. And we hear that because of COVID-19, there are more people are depressed, and suicide rates are increasing, and divorce rates are increasing. I read that actually yesterday. And so with technology, we can be connected with people. As a result, we can hopefully, it'll help our mental health, and it will also help, maybe, help us. I'm not saying it's a cure for depression. I'm not a psychologist, by the way, and I'm not a medical doctor, and I'm not a psychologist. So what I'm saying is, I like connecting with people. Why am I giving these presentations, right? Because it's one way of connecting with people and posting it, and one way of speaking to, in a way, the outside world. And so those are things. Because of technology, we can do all these things. So as a result, but then all of these technologies could be attacked. And so there could be attacks that's going to, that could, if my Zoom presentation, Zoom is attacked, right? And it can go and through Zoom can come into my machine and observe all what I'm doing. So we have to make sure that all of these technologies we are using, because we are going to rely more and more on these technologies. So we've got to absolutely make sure that these technologies are indeed secure as new technologies are developed. And again, we are still using old technologies and new technologies, and these technologies must be secure. So we've got to do our very best. And I don't believe in 100% security, right? Because it's impossible. I mean, can you guarantee 100% health? No. There's some way or another, there could be some problem. Maybe one day your blood pressure could be a bit low, or your blood sugar could be a bit high. So something or another, but we've got to be as secure. We've got to have all our systems and technologies as secure as possible. So with that, I want to end this presentation, and I'm going to also continue with this series, and tomorrow I'll be also giving another presentation, and that's going to, I'll think about it, because there are 3 or 4 topics that I want to talk about. And again, these are all based on my past presentations over the years. So anyway, so that's going to be tomorrow. But again, we have so much of work to do, and in a way, so much to look forward to, because there are these vaccines that are there. And so we've got to, we must have hope. And while we are working from home, we have to do the best we can. So that's how I think of it, right? In the sense that I look at it as, that this opportunity is never going to come again for me, right? Hopefully, and I hope it will never come again, meaning that we are not going to, there's not going to be another pandemic, say 5 years down the road or 10 years down the road. So I hope we will not have this situation again. That means this opportunity will not come again. And I hope this opportunity never comes again. But while we have this opportunity, there are so many things that we can do, study and learn. And so that's, and that will keep us sort of in good spirits, and in a good situation where we can, contribute more. So with that, I will leave you for today. And again, thank you very much for listening to this presentation. So I'm going to stop recording now.